Okay, so in this lecture, I'm going to cover section 4.83, which is called the hypergeometric distribution or the hypergeometric random variable. This is the last of the random variables, specialized random variables we're going to discuss. And so I'm going to introduce it, we'll do some examples, and then derive the expected value and the variance. Again, there's a lot of calculation involved, so be patient. Okay, so the difference, so this is 4.83, and it's the hypergeometric distribution. The key difference between this one and the previous ones we've been discussing has to do with the fact that now we are sampling without replacement. Okay, so it's not a Bernoulli trial. The experiment is changing each time it's being performed. So the setup, which we'll do concretely, will be an urn where you have n balls total. There will be little m white balls, and therefore n minus little m black balls. So two colors. Okay, and we're going to draw lowercase n balls and from the urn. Okay, so the sample size is n. Okay, little n. And then x, our random variable, will be the number of white balls selected in our sample. And this, the sampling is done randomly. So what's the PMF for this? Well, that would be, let's say P of K, that's the probability that X has value K. So let's figure this out. First of all, how many balls are there? They're uppercase N, capital N. And the total number of ways of selecting is big N choose little n. Those are the total number of ways of choosing little n balls from a set of big N balls. Okay. Now, how many ways can we choose K white balls? Well, there are M white balls in the urn, and we're choosing K. So this is the number of ways of choosing exactly K white balls from the urn. And we still have to choose the black balls. So how many black balls are there? N minus lowercase m. And we're choosing n minus k. The remaining balls in our sample have to be black. So this would be the numerator of our fraction. So now let's note that this depends on three parameters, n, little n, and little m. So that's important. And here k is 0, 1, 2, 3, 4, etc. Okay, so here's an example. So let's draw 6 cards from a standard deck. So 52 cards, and without replacement. And find the probability of obtaining 2 hearts. Well, let's figure out what these parameters are. Capital N is 52. And little n is, we're drawing 6 cards. That's a sample size, that's 6. And little m, that's the number of successes or the number of whites in the original formulation, but now that's the number of hearts in the deck, and 1/4 of the deck consists of hearts, so 13 out of 52. And then what is k in this case? K is equal to 2. That's the probability that X is 2, right? 2 hearts. So now we can just stick it into this expression. And what do we get? We get the probability of 2 hearts, which is P of 2, is given by 13 choose 2 times 39 choose 4 over 52 choose 6. And that's going to be if you calculate this on a calculator, 0.31513. So that's the answer to this problem. Okay, so let's do another example. So this is the second example. So we have a batch of integrated circuits. In other words, chips, computer chips. Let's just call them ICs. And 20% are defects. Okay, so we take a random sample of 10 chips. So we draw 10 chips, and let's find the probability of having 3 defects. Okay, so here there are, so I should have said 20 integrated circuits. That was the original number. Maybe I said it, but I didn't write it. Okay, so N would be 20 in this case. And the number of, there are 20% defects, and we want the probability of a certain number of defects. So 20% of 20 is 1/5 of 20. So that's little n is 4. Okay. And what is k here? K is 3, the number of defects we want to select. So what is the probability of 3 defects given by? Well, it's given by 4 choose 3 times 20 minus 4, which is 16. That's the remainder. 10 minus 3 over 20 choose 10, right? Because we're doing a sample of 10 from the 20. And you can calculate this, and what you'll get is 0.0583. So only about 6% of the time you would expect, the probability is pretty small of having 3 defects in the sample. Okay, so in the remainder of what I'm going to do is just compute now the expected value as well as the variance of this distribution, of the hypergeometric distribution or the hypergeometric random variable. By the way, we should have made a definition. Any random variable with PMF, which is given by P of K equals M choose K, N minus M choose M, N minus K. over n choose n is called hypergeometric of type, well, it depends upon three parameters, n, and m. So that's the these three parameters determine the actual distribution. Okay, so let's now compute the expected value and the variance. So let's assume that X is hypergeometric of type capital N, lowercase n, m. So now what is the expected value of X to the power of k for some integer k, non-negative integer k? Well, by definition of how we defined expected value, that would be the sum. Let's use j equals 0 to n. Okay, so by the way, you can't choose more than, your sample size cannot be more than the total number n. So we only go from 0 to n in this expected value of j to the power of k times p of j. Okay, so that's what it is. You can't go bigger than n. It doesn't make sense. Okay, so now what is this? This is the same thing. We could have used instead the sum, since at j equals 0, it vanishes. J equals 1 to n, j to the k, p of j. And now we substitute the value of the PMF. So this is going to be the sum. J goes from 1 to n of j to the power of k times m choose j times n minus m choose n minus j over n choose n. Okay, so that's what you get so far. And now I'm going to have to make use of identities I've used before, which I'm going to put over on the side here. So I'm going to use the fact that j times m choose j is equal to n times m minus 1 choose j minus 1. And the same similar identity, just different parameters, n choose n is given by capital N, n minus 1, choose n minus 1. We've used these before. Okay, so I'm going to use that here. So I'm going to make some substitutions. Okay, so okay, so I need room. So it's going to be the sum. J goes from 1 to n, j to the k. Now m choose j by the first identity is m over j. Oops. The fraction m over j times m minus 1, j minus 1. And then I repeat the binomial coefficient which comes after. And then the bottom is n choose n, but n choose n is, by the second identity, is n over n of n minus 1, choose lowercase n minus 1. Okay, so now what does this do for us? What this does for us, we can bring out some constants, the m over j and the n over n. Well, the j cancels with the j to the k. So this becomes m times n over n. The sum, j goes from 1 to n of j to the power of k minus 1. Okay, and then you have m minus 1 choose j minus 1 times n minus m, n minus j over n minus 1 choose lowercase n minus 1. Okay, so that's where we are so far. And the rest of it is just now to do a little bit of rewriting. So let me pull up a new. Okay, so I have just rewritten at the top what we had derived on the previous slide. And now I'm going to set L equal to J minus 1, or in other words, J equals L plus 1. So what do we get? It's Mn over N. The sum changes. It's not J anymore, it's indexed over L. So if J starts at 1, L starts at 0, and it goes up to N minus 1. And then we get L plus 1 to the K minus 1. M minus 1, choose L, and then N minus M, choose N minus 1 minus L, over N minus 1, choose lowercase n minus 1. Okay, we're nearly there. Okay, so now we stare at what this is. And if this were an L instead of an L plus 1 here, this would be the expected value, this expression, of another hypergeometric distribution. It would be y to the k plus 1, where y is of type n minus 1, n minus 1, m minus 1. But it's not that because we have this L plus 1. So to correct for that, we put the 1 over here, and we would get the mn over n, the expected value of that expression. Okay, so let me summarize what I've done so far. So this is what we had from the result of the previous calculation. We get what is called an inductive formula. And from this, we can compute immediately the expected value of the hypergeometric random variable x, because the right side is m times n over n times the expected value of something to the 0th power. Well, something to the 0th power is 1. The expected value of 1 is 1. So we obtain, first of all, this formula. Secondly, we can actually compute the expected value of x squared, and the expected value of x squared, the second moment, in other words, is mn over n, the expected value of y plus 1. But what is the expected value of y plus 1? That's going to be the expected value of y plus the expected value of 1, which is, of course, the latter is just 1. And we know what y is. Y is Poisson. Oh, I should have written a y there, not x. And this is going to be mn over n times, now we apply the formula for the expected value of y. We know that it's given by m minus 1 times n minus 1 over n minus 1. And then the contribution of the 1, we put it back in, and that's what you get. Okay, so this is sort of a mess, but now we can compute the variance of x. And the variance is given by this expression we just computed minus the square of the expectation. And I'm going to spare you the details. I'm just going to write the answer. It's going to be m n over n times what times m minus 1, I'm just doing the substitution now, n minus 1 over n, capital N minus 1, plus 1 minus the square of this m n over n term. Okay, so it's a bit of a mess. And you're not going to be able to remember this. Who's going to remember this? But I'm going to box it. Okay, so there you have it. So far, I'm just going to make one more comment about how to think about this. Okay, so if we go ahead and try to make the following substitution, let's think of. So what does m over n represent? Remember, m was the number of white balls in the urn and n was the total number of balls. So if we set this equal to p, lowercase p, this is the probability on the first draw of selecting a white ball. Or did I say black ball? Selecting a success, let's say, of success on the first try. Okay, so therefore, what do we get in this case? So then the expected value, if we stick this in to expected value, we'll get this as p times n. So this is sample size times the probability of selecting on the first draw a success, whatever the success was, I don't remember. Okay, and then what does the variance become in terms of this new variable? Well, it would be n times p. Actually, usually it's written in n times p. It would be n times p. If you do the substitution, it's n times p times 1 minus p times 1 minus n minus 1 over n minus 1. So this is an easier form of the expression. And let me point out something very interesting. So if n is very large compared with lowercase n, the sample size, so you have a very large population you're drawing from, but the sample size is small, then notice that then n minus 1 over capital N minus 1 is small, very small. So therefore, this term that occurs here is approximately 0. So therefore, the variance of x under this approximation is np times 1 minus p. We've seen that before. This occurs for the right side is the variance of the binomial random variable. And in fact, the expected value here is also the expected value of the binomial random variable. So how do we interpret this? We interpret this as follows. If you're drawing without replacement from a very, very large population and your sample size is small, what this is telling us is that you can pretend for small enough sample sizes that you're drawing with replacement. So that's the, even though they're not the same, for small sample sizes, we can pretend it's like the same because the population is so large. And that's where I wanted to end this today. So in other words, for very large population sizes and relatively small sample sizes, the hypergeometric random variable is approximated by the binomial random variable. So that's it for today.